All right, we're ready to do our last section. And because I want you to get used to doing implicit differentiation with any variables, not just y's and x's, we're going to try a couple here where you do implicit differentiation with a variety of different variables. You'll notice this first problem actually has 3 different variables in it. Well, can you do that? Yes, you can. So, the key thing is to focus on what it's telling you to find. It's saying that you should find dA dP. The key thing to know is which variable is your normal variable where you don't have to do anything special. And that's always the variable on the bottom. We're doing the derivative of A in terms of P. So P is our normal situation. If we do the derivative of any other function, any other variable, that is not a P, we'll have to do a little chain rule on it. P's get treated like normal. They get treated like X's. So, let's give it a whirl. So if I said do the derivative of 3r to the 7th, you would say, no problem, 21r to the 6th. Okay, I did the derivative of an r. Is r my normal variable? No. So therefore, if I knew what r was in terms of p, I would have to chain rule it and do the derivative of the inside. So in this case then, since I can't do that, I have to say, okay, I would do the derivative of r in terms of p if I knew what it was. So I have a dr dp here. Okay, moving to my next term. 6a to the 5th, derivative is no problem, 30a to the 4th. That also is not a p, our normal variable. So I would have to tack, in this case, a dA dP on the end, since A, I was doing the derivative of A in terms of P. Okay. My third term is a P, so it's normal. I don't have to do a chain rule. It's just minus 4. And then over here, I would have 7P to the 6th. Also, my normal variable, I don't have to do a chain rule. I know it. This whole thing is being defined in terms of variable P. Okay, now you need to go back and solve for what they asked you to solve for. In this case, it said find dA dP. I only see one dA dP up there. So we're going to isolate that one ADP. We're going to throw everything else over on the right-hand side. So I'm going to leave the 30a to the 4th here on the left. I'm going to leave the 7p to the 6th over on the right, add 4, and then also have to subtract the 21r to the 6th dr dP. And yes, you can have a dr dP in your solution. It's okay. Last but not least, to get dA dP by itself, I need to divide that over. So I'm going to end up with dA dP is defined to be 7p to the 6th plus 4 minus 21r to the 6th dr dP all over 30a to the 4th. And double checking that there aren't any common factors. I don't see any numbers that are common, and I certainly don't see any variables that are common. So that would be our solution. Okay, our last problem. This is where implicit differentiation actually leads. After we finish this chapter, we'll be moving to some application problems where you actually put derivatives to use for real-world situations. And that when we do that, we're going to be finding rates. Now, I'm sure as you've all learned in physics, a rate is nothing more than the change in a distance over the change in a time. So therefore, when we want to work with rates, we choose to find derivatives that are something over dt. Because right here, when I have dy over dt, that would be the change in y over the change in p, the time. So it would be the rate, that would dy over dt represents the rate that y is changing. Since dt is on the bottom, that's our normal variable. So only t's, if we do the derivative of t, do we do just a normal derivative. And since you'll notice we have not a single t in this problem, every one of these is going to have a something dt on it. So in this case, I'm going to go All right, that's 12x squared would be my derivative. It's not a t, so I'm going to tack a what on it? And yep, I would tack a dx dt on it. Plus, derivative of 2y to the fifth would be 10y to the fourth. It's not a t, so I would have to tack a dy over t on it. And last but not least, the derivative of cosine of x would be a negative sine of x, also not a t, so it too would have a dx dt on it. Okay. You need to look back at the problem and find out which one they wanted you to solve for. They wanted us to find an expression for the rate of y, dy dt, so we need to isolate dy over dt, which means I am going to throw the 12x squared over to the left side and have a negative 12x squared dx dt minus the sine of x dx dt. And then I will be dividing over the 10y to the fourth. Once again, is there a common factor I can pull out? So the top has a dx dt, the bottom doesn't. There's no numbers in common to all three terms, no variables in common, so no, we cannot reduce that one. You could, if you wanted, pull dx dt to the front or the back and say it was negative 12x squared minus sine x times dx dt. That would be okay, but it's not essential. What we'll be doing with this in the next section is we will actually be representing a situation such as one of the problems we'll do if we have a barn here and a ladder leaning against the barn, and the ladder is sliding down the wall, which means the top is getting lower, the base is sliding outward, and we want to know how fast, if somebody's up here on the ladder, at what rate are they falling? So we can actually do that by simply assigning variables to our situation and say our ladder is 10 feet long. We can do a basic Pythagorean theorem, and then by finding, if I want to know the rate the ladder's coming down the wall, I can try to find the rate of the wall would be dy over dt. I can solve for dy over dt. They'll give you some numbers to fill into this formula, and you'll be able to figure out the rate it's falling. It's very, very cool what you can do with rates with this particular concept. So we'll be coming back to use implicit differentiation a great deal in the future. While it may seem like strange variable manipulation right now, it has a lot of uses. So now, you all get the rest of the time to work on your homework, or you can work on your portfolios if you need to, since they are due on Friday. I expect you to be worked there. If I get a report that you guys were goofing off or being a pain, there will be swift and sure retribution. There is an extremely likely chance already that you will get a quiz over this particular topic. And if I get a bad report, it could become a very mean quiz. So use your time wisely and be productive. If you have questions, you know where to find me. Seminars are always a good time. If I can, I will try to post this audio file if you needed to rewatch it. I'm not sure if that'll work or not, but I'm going to give it a shot. So good luck with your homework, and I'll see you Friday. Actually, I guess I'll see you tomorrow at seminar.